kinds of input and output devices, so we have to learn those symbols, create ladder logics using standard relay logic rules, place comments and on relay logic devices that uses standard rules, create relay logic circuits for process and industrial control problems. I think this is, let's go back, I think this is chapter 5 in your textbook. Yeah, we'll make sure. If you wanted to go in there and read that, if you got your book already, it's always better to get one topic through several different type methods. So a lot of people read better than they listen to lectures. A lot of people like lectures better than reading, and a lot of people like lectures and they reinforce it by reading the chapter in the book or vice versa. It should be opposite. You should read the chapter in the textbook, and then we lecture on it, and we reinforce what the textbook, and then we make, of course, comments in addition by having a lot of experience in the trade, which I do. So relay logic, sometimes called elementary diagrams. I've never heard it that. Line diagrams, I've heard it called that. Relay logic diagrams, I've called that. Or relay logic, ladder logic, or simply ladder diagrams. I've heard it, or ladder logic. I've heard it called that, but I've never heard it called elementary diagrams. For here on out, we're going to call it relay logic diagrams. Uh, I might call it ladder logic. That's what I've learned in ladder logic. We'll see when we talk about that a little bit. First step is creating the program for the PLC, and that's not true. It depends on what you're going to do. Most of your original PLC programs were converted over from relay logic. But seldom do we do that anymore. Normally we start off with a PLC and we write the program for the PLC. Very seldom do we actually draw up all the relay logic and then come over here and take that relay logic that we spent all this time on and convert it over to a program. So normally what we do now is we do the program, according to what type of inputs we have and what type of things we're supposed to control. Show the symbols for the different output devices. So when you draw these ladder logic diagrams, you've got to understand symbols. And you've got, so on the PLC input, we have very few symbols inside the program itself. But when you hook these input devices up to the PLC, or you hook these output devices up to the PLC, these are going to be usually wired by electricians. Electricians know these symbols, so you have to use the symbols on the input and the output that's used by the electrical trade. So we'll learn symbols. We got to learn symbols in this class. So one of the things that we'll definitely do when we go back and look at inputs and outputs, we'll look at the symbols. We don't really need them for our PLC because what we do on our PLC, and we can do that, by the way, and we have a box that we have set up so we can literally hook things to the PLC. So this is the outputs. This is the inputs at the top. These are the outputs at the bottom. And what we have is we have this wire down to this edge trainer. I think the other day I said it was put out by Allen Bradley, but the edge trainer is put out by Festo. And so this is what we're going to use for inputs right here. There's a program in it right now. So these are what, and we can use them as momentary switches, which we use a lot, or we can use it as a permanently pressed switch. If we wanted to hook this up, and I'll show you all the panels that we have made up, we would do the same thing down here on these female banana plugs that we would do if we were doing it up here on the PLC. It's just that it's a lot easier to wire down here. This is the outputs over here. What we're going to be doing is the trainer has a light emitting diode that comes on when that output is true. So we'll be using that a lot. So we'll say turn on motor 1, and if we assign it to this output right here and it comes on, then that'll assign it off. But in actuality, you would have to hook this up. The motor, you would have to hook hook it up from this blue one over to here with the motor in the center. And then, of course, well, not necessarily the motor. It might be the relay that controls the motor. So very seldom do we run motors directly off the PLC. Normally what we'll do is we'll have the PLC pick up a relay and then, or energize a relay, I should say that, and then the relay runs the motor. And I'll show you all a little thing. If you don't know what a relay is, you got them. I mean, you got them out there in your car. So, like I said, when you hit the little button on the little button on your steering wheel or something to turn on your lights, there's no way that those things are probably on a 20 amp fuse. They probably pull about 10 amps, and there's no way in the world those lights are going to be run by that little switch in there on your car. So what it does is when you turn on your lights, it goes to your module control computer. It has a relay that it energizes, and then the lights are turned on by that. Also, the starter on your car. The starter on the car probably draws 70, 80 amps at least when it's warm, and you're turning it with a little key on the dash, or you're pushing a little button if you got one that's got a fob on it, and there's a relay out there. We call it a starter relay. That we take that little 12 volts coming off the battery, and we hook it up to a coil, which energizes a relay, which can handle that current. After relay logic is drawn, it is converted to PLC ladder diagrams, often called ladder diagrams, and that's not necessarily true. Ladder diagrams, this is the primary. There was actually, I think there's actually 5 programming languages that's available for PLCs. Our PLCs only supports ladder. Your newer PLCs usually support at least 2. Some of them support all 5. And when you create the program in the application, you tell it what language you want to program the PLC in. So the Compact Logic, I think, supports 4 languages. And of course, the primary language used in the United States, probably to create over 90% of the programs, is this programming language we call ladder diagram or ladder logic. So that's what we teach. You'd have to take a lot more advanced class if you're going to move into structured text or function block or these other diagrams. Of course, function block, if you take digital, you'd say, oh, okay, so it'd be easy to program that. So if you already have digital. Voltages between 2 rails labeled L1, L2. This is not always true because it gets very confusing, and I'll show y'all on the U.S. Steel prints. But usually the power rails are going to have some form of L1 and L2. I think on the U.S. Steel prints they call them PCL1 and PCL2. So the relay logic usually has the 2 power rails where we connect our circuit between are going to be some form of L1. L1 and L2 has been in every one of them I've ever seen, but they might not be L1 and L2. This gets really confusing when you take motor controls, so we correct that because our 3-phase power is labeled L1, L2, and L3, and then our control powers, if we want to label that L1 and L2, students get confused. So when I teach the class, I call them CL1 and CL2. But what we do is we draw the diagrams between L1 and L2. And we can have a lot of them, we can have a few of them. Got to have at least, and the circuits themselves are referred to as rungs. So we got to have at least rung, but we can have many rungs. I'm going to show you a portion of a diagram that was provided to us from U.S. Steel, and the section I show you is on page 137 of a relay logic diagram, and it references contacts up in the 200s. So you can imagine these guys can get very, very complicated depending on what function they have. So basically, we have a symbol. This is our first symbol. So let me see if I got that in here. I thought I did. These things, then they would think it was a resistor. Uh, okay. So we're looking at these, right? We was talking about the symbols. So this is a symbol of a coil, and we call it a coil. We call it a relay coil. And that's we energize the relay coil, and the contacts controlled by that coil change. We'll have at least one contact, but we can have multiple. I think I told y'all we've got one over in the motor control lab. It's got 8 contacts on it. So this is a diagram. This is I don't know where this one came from. I got a little better one that they're doing. So they're calling it L1 and L2, but we'll look at the U.S. Steel print and look at that. And this is AC. These are AC relays because they have a transformer right here. It's double fused, which is very popular in the industry. But here's the relays, and all the relays have names. And of course, these are rungs. This is a better print. This is the U.S. Steel print. This was given to us. We call a class for U.S. Steel. They came out here 8 hours a day for 2 weeks. They had a training up in the it's up on the hill. You can see the building. It's still up there. Even though it don't belong to U.S. Steel anymore. But they did their training up there, and they would send those, and it was all computer based. So they'd go up there, and they would sit in front of a computer screen, and they had like 15 people go through that program for a year, and I don't think but one of them passed the test. so, so they decided something to do. So they took them people offline. They sent them out here. Nancy was here. Then we had a couple of people that's not here anymore, and we did 8 hours a day for 2 weeks. They were paid while they were here, and we had to teach our classes around it. It was really a unique situation. But when we got through with that in 2 weeks, everybody but one passed the test. So I think U.S. Steel still pays for their students to come out here, but it's almost impossible with rotating shifts because they all rotate. Well, what we have here is these are relays. This they're calling theirs PCL1 and PCL2, and then the circuits are drawn between L1 and L2. So this right here is one rung. Should do that with repeat. Now, what we're doing though is just like we showed y'all, is we are assigning every relay is assigned a name. So here they didn't have a room inside the coil, so the name of this relay is 5B1EB, which makes a lot of sense if you knew this thing that what it runs. And of course, this is 5B1E. This is 5B2DD. This is 5B2H. This is 5B3D. And of course, this right here is one rung. And it's got multiple loads, but they're connected in parallel. So it's legal to have parallel control devices go between L1 and the load, and then the load goes between L2 and the control devices. So the loads are on the left in the rung, and the control devices are on the right. And then we'll come back in a minute and look at the way we reference things. Control rules, accept the standard, create relay logic, the rules. So what the rules in the textbook is not exactly right. So I'm gonna give you a handout. You can print it off. I don't forget which section it's in. But I'm gonna give you the rules that I know for relay logic, and I've been dealing with relay logic for a long time. Control devices such as switches, push buttons, relays, and sensor contacts must be played. This is relay contacts, guys. I think that's a bad mistake. Go ahead and make that correction right. Oh, it won't let me in. Oh, I know what I got. I know what's going on. Up through two, right? So if you have a line that lines up horizontally, it gets the same number. So what we see here is what we draw. So what we see here, if y'all can see my cursor, is that this line is line 1 on page 37. So the 37, it just says that this is the 37th page. This is line 1. Okay. But this is a rung, but it's got multiple lines. This is line 2. But we got another line that lines up horizontally with it. It does not have a line number, so it's the same as line 2. So any line that lines up horizontally gets the same number. So here's line 3. So this would be line 3, and this would be line 3. This is line 4. So this right here would be line 4. This would be line 5. This would be line 5. This does not line up with anything. So this guy right here is line 6. So line numbers go to the left of L1. We don't number rungs, we number lines. So a rung consists of one or more lines. In motor controls, PLCs, we don't number lines, we number rungs. So that's a big difference right there. So in motor controls, we number lines. We don't number rungs, we number lines. Now why we do that is these things, and this is just a partial, I've clipped this off. Why it's done that way is that this relay right here, this 5B1DB controls contacts. Those contacts could be anywhere in this diagram. So we got to have some way to indicate where these contacts are. And that's what this is over here. So that says this relay has a contact in line 13702. So I'm going to come at 13702, and I'm looking for a contact that has the same name. So there's the contact that's being controlled by that relay. So when I energize that coil, that contact closes. And when that contact closes, it's going to energize 5B1M. 5B1M's got a relay, got a contact in 137.2. 137.2. Sorry. Oh, I'm sorry, 137.7. So 137.7, and there it is right there. So using line numbers, it allows us to tell where these contacts are that's controlled by that relay. By the way, if it's underlined, so we separate them with commas. If it controls multiple contacts, so this relay out here controls multiple contacts. This means I'm looking for a normally closed contact. A normally closed contact is the symbol that we showed y'all before. So it's got a line through it. So I'm going to come over here and see them on this print, but they cut them off. So that's line numbers right there. And notice line numbers are on the left of L1, and then contacts are given names. This is not a light bulb. It's in parallel with this relay coil. So anytime that we energize this coil, this light comes on. So there's a symbol for a light bulb, but you gotta know that, right? This is a symbol for a selector switch. This is a symbol for a push button. It's a two position. It's got it's a normally open, normally closed. They're mechanically connected. This is a limit switch. This one you can't really tell. You can't really see. I need to blow this up as much as I can. So these are symbols that we have to learn. Now I have no idea where this guy right here goes. Can you see this light right here? I can't read where it says it goes, but it goes somewhere. Because if it didn't go somewhere, it wouldn't work. So that's the way relay logic is drawn correctly. These are comments. So anything we got comments about, you can tell what US Steel did is they actually gave you what this was. So 5B, 1DB was number 5 bridle, number 1 dynamic braking resistor. Braking, not dynamic braking contactor. So what they're doing on their comments over here is they're telling you what each one of these mnemonics that we're using for the relay coils, what they stand for. Bridle was a group of like 7 motors, and the strip would chain through them, so it would get really, really good torque. And they would call them bridles, and there was quite a few of them on this line. It was a galvanized line, so it actually put the zinc coating on a strip for galvanized metal that you could buy it, and then they had a special line they would run it through and put the grooves in it for galvanized roofing, metal roofing that's got the shiny tint to it. So this is relay logic, and I think that's what we're going to see in some of these rooms. So output devices such as relay coils, lights, small motors, and solenoids must be placed between the control devices and L2, or what we call it. One and only one output can be placed in each line. A rung is an electrical circuit that runs between L1 and L2 that consists of one or more lines. Magnetic motor starter contacts are the only ones that allows something between the motor starter coil and L2. The problem we have with motors, so if I had a motor starter, how'd you draw it? I think I did. I got it. Probably got it. So a magnetic motor starter, it would come over here and have this, and then over here it would have an overload coil. So what happens is the motor comes down, and we would have the contacts out here in another circuit. This would be 3-phase. And then we'd come down through here and we put what we call an overload sensor that senses when the motor draws a lot of current over time. So the problem we have with motors is when we start them, they draw about 6 to 8 times. So up here I might have a fuse. Now that's a bad symbol down there. It's okay, it's good. So let's say our motor to run it took 10 amps to run it. When we start it, let's say on the low end, it's going to try to pull 60 amps just to get it started. But my fuses are going to have to be rated over 60 amps. It's usually 150 to 155%. So these things might be rated at 70 amps. But what happens if the motor stalls? Is the fuse going to blow? No, because it'll pull 60 amps. My fuses are rated to allow it to start and then give it some overhead, so the motor would sit there and burn up. So what we have have is we have these sensors in what we call a motor starter that senses over current over time. So what it does, it lets the motor start, but if the motor don't start, then these sensors will sense it. It'll open this contact up, and let's say this is M, and these down here are M. It'll open up M or make M drop out or de-energize and pull power off the coil. So the only thing that's allowed on relay logic, the only thing that's allowed between a load and L2 is an overload contact. And it's going to only, so you can tell if a coil is a motor starter because it's got an overload out here. It might be labeled overload, by the way. So that's the only thing that's allowed between L2 and the load is an overload contact for a motor starter. Only one output device can be connected in a rung. The rule is one or more output on a rung, but only one output per line. There are no multi-load series or series parallel circuits allowed in relay logic, and that's also true, by the way, in PLC logic. So a lot of the rules that we're looking at here apply to a program in a PLC. So Rule 5, control devices such as switches, relays, sensors with a single contact can only be used once in a relay logic program. Control devices that have multiple contacts can be represented multiple times in a relay logic diagram. In other words, the same contact can only be used once. So if my relay's got one contact on it, and we come over here and we use it in this line, we can't come down in another line and use the same contact because it's only got one contact. But like I said, we've got relays that have a lot more than one contact. So the other contacts could be used someplace, but that one contact can only be used one place. Each relay must be assigned a name. The name should be written above each rung load. The name is usually an abbreviated version of the function of the load within the control circuit. So a lot of ours we call CR, which means it's a control relay. M, which would be a motor starter or a contactor. But when you looked at the USCL prints, you noticed they had more detailed names that would not fit inside the coil symbol, so they wrote those above. Rule 7, each contact controlled by a relay must be given the same name as the relay that controls the contact. And we just showed y'all that in our example. Rule 8, an output device can only represent once in a diagram. So I can't come up here and have M, call this M1, and then another rung down here somewhere say M1 again. That means that coil, that we got the same coil and wired two different ways. So we can only represent it once in the diagram. So each contact controlled by the relay must be given the same name as the relay that controls the content. I think I went past that. All control devices and output devices must be placed horizontally. So I see people draw them real weird. But that's not the way it's supposed to be. You're supposed to follow the standard. So you got L1 and L2. We have no curved lines. Every line is straight. We can make 90-degree turns, but we can't make arcs or anything inside a ladder diagram. And that's also true inside of almost every diagram I've ever seen. We don't have arcs. The only place I've seen it is in house wiring or commercial wiring, where they're pointing back to the panel blocks. Signals in a relay logic must flow from L1 to L2. Signal flow must never flow back to L1. In the book gives a pretty good example of that later on. Diagrams should be numbered and commented correctly. Unlike PLC diagrams, horizontal lines are numbered and not rungs. So in relay logic, we number lines. In PLC, we number rungs. Alan Bradley calls them rungs, just like we learn Siemens calls them networks. So if you get into a PLC, every one of your rungs they refer to as networks, and they'll call them network 0, network 1, network 2. But here we'll refer to them as rungs. I'm just getting you said if you get into that PLC. Horizontal lines are numbers are not rungs. Line numbers are placed to the left of L1 adjacent to the line. Any line that aligns horizontally with another line gets the same number. Comments can be written to the left or right of the diagram. All the ones that we show y'all, they're actually on the left on the L1 side. The location of each relay contact controlled by a coil is identified by writing the line number of the contact location to the right of L2 and adjacent to the coil symbol that controls the contact. Multiple contact lines, the numbers are separated by commas. A normally closed contact location is underlined. These numbers are referred to as numerical cross-reference numbers. And most people just call them cross-reference numbers. Well, I think I've got the US Steel print here again. I don't need to go back. So here's the US Steel print. Yes, ma'am. No, no. If you looked at the when we started this, Janice, I said these are we call them revised rules. These are the rules right here. So the book don't quite do it right. So this handout should be available in this section, and also when we come into class, we're going to be on campus next Monday. By the way, this is Monday. Next Tuesday. Thank you, Janice. We're going to be in class next Tuesday, and I'll give you these handouts. So I'll give you these revised rules, which is what they go. So the author of the book is really good, but I've written textbooks before, and and then you'll come back later on after it's been published, and you'll say, "Oh my goodness, I should have said this." So yeah, I'm gonna give it out, and you can see mine go in line with the actual diagrams that I'm showing you. The book doesn't even do that. It don't talk the book. The book don't even talk about lines. But the two diagrams that I've showed you, it's split. The rungs are split up in lines. So this is what I'm doing. I'm going back and actually telling you what I know. And I don't think I've ever taught out of a book. Well, there's been one where I didn't have to supplement it, but it was a book that I wrote. Every book that I've ever used, I've had to revise a little bit. Even the PowerPoints that I provided, because I've been in the field a long time, and I know a lot about the way things are, and not what somebody that hadn't worked in the field for all these years and doesn't actually know what it is. Because he'll use terms even inside his book that we'll have to come back and correct. Because if you get into the manuals that goes with the PLCs, and the author calls them registers, and you get into the manual and they never even mention the word registers, then it's going to be a little confusing. Because our main source of information, guys, is books are nice, but every PLC on the market, the creator, the manufacturers, especially Siemens and Allen Bradley, I don't know about other people, but they give you all the documents. They give you all the documents on all their PLCs, and they give them to you free. And of course, they give them to you free because if you're an engineer and you buy a PLC and you've got all this information, then odds are you're going to buy the PLCs that you got all this information on. So that's very important. That's a good point. So that's why I call these the revised rules, because these are not exactly the ones that's in the book. So the ones in the books don't talk about wire numbers. They don't talk about contact numbers or anything like that. But what I'm trying to do is, tell you what you're going to see when you get out there. So every print I've ever had, and if you had motor controls, we require you to do this. We require you to set your print up, your line diagram like you'll see in the industry, so you'll get used to seeing with that. So that's a real good question. Thank you. So yeah, you're right. So we're going through We went through how many rules? 12. The book has 9. So, well, like I said, they don't talk about the book. The guy don't talk about line numbers because he's PLCs. So in PLCs, we don't have line numbers. So this guy's got all this experience in PLCs, but he don't have all this experience in relay logic. So he don't talk about line numbers. He don't talk about contact numbers, and he doesn't do anything like that. So that's why I'm supplementing this for you. So when you get out in the field and you start looking at these diagrams, you know them. And so when you take motor controls, whoever teaches it, even Mr. Foster, he's teaching it this time. He should make sure that y'all understand this. So if you got this, if you took motor controls, you get all this. And so from the look of it, it looks like this guy came up through PLCs. He didn't come up through actual true relay logic. So that answers your question? You okay? Yeah, so we'll hand these out. So like I said, if you wanted to run them off, they're up there. They should be up in that section. If they're not, you need to let me know. And I'll give them to you when you come in next week on Tuesday. And if you lose them, there'll be a section up there that you can use because this is what we'll go by. And we'll apply these to PLCs. So PLCs, like I said, they don't number lines. They number runs. They don't provide contact numbers for you. So that's something that you're going to have to really understand. That when you document it, you might draw out the print or print it out. So all these ladder diagrams that we program, we can print them, and then you might want to put those contact numbers out, those contact cross-reference numbers out there, and so people would actually understand it a little bit. I've never seen that. Creating relay logic. Let's see. Clearly define the control problem. Draw the schematic diagram of the system. Set up. Discuss the problem. Review and follow the 9 or the 12 relay logic